Welcome back, class. Today we're going to discuss the topic of mixed numbers. Over the past 2 weeks, we have truly mastered fractions. We know how to add, subtract, multiply, and divide fractions. Furthermore, we know how to perform certain operations between two or more numbers, depending on the circumstance. We know how to, for example, calculate the GCF and or perform prime factorization of a given number in order to simplify a fraction and find the simplest form of a fraction. We know how to, for example, calculate the LCM of two or more numbers if we wanted to, say, add or subtract fractional terms more efficiently than, say, finding a common denominator using the multiply by the opposing base method. And so we've truly mastered the art of being able to manipulate and or work with fractions. There is one tiny problem, and that is what happens when we actually go to use fractions in the world around us. So, for example, suppose we are an engineer or we're a foreman and we performed a bunch of different addition and or subtraction as well as multiplication and division operations which utilize fractions. And suppose that at the end of the day, we found that for a worker to do their job, they need to construct for us a device that is exactly 63/7 of a foot long. Or for the Europeans and or people from different countries who may not necessarily be that familiar with the feet and inches American system, they may be familiar with say SI system of measurement. So maybe they're more familiar with, say, a worker being tasked with measuring out 63/7 of a meter. And of course, the Americans or the Europeans or everyone is going to be sitting and scratching their heads. What do you mean 63/7 of a foot? Or what do you mean 63/7 of a meter? That makes no sense. And of course, it makes no sense. But what we have to remember is that at the end of the day, after we've performed all of these different operations using fractions, and we might be presented with some sort of an improper fraction, as is the case here, the improper fraction just stands for a division operation. So 63/7 stands for 63, the number being divided into 7 equal groups. And of course, you can go to the side of your page and do the division operation. We know that 7 doesn't go into 6, but 7 will in fact go into 63 9 times. 9 times 7 giving you 63. And when you perform the subtraction operation, you get a remainder of 0. So instead of confusing your workers, instead of telling your welder that he needs to weld a piece of steel that's exactly 63/7 of a foot long or 63/7 of a meter long, instead of telling your construction worker he needs to measure out something that's exactly 73 or 63/7 of a foot long, you could have instead told them you need to measure this object that's exactly 9 feet long. Okay? This brings us to the topic of mixed numbers. Now, in our modern world, because of certain technological and social innovations, as well as innovations in mathematics, specifically computing, digital electronics, and the invention of the what is known as the positional decimal, which we'll talk about next week, you will likely not encounter mixed numbers outside of this class if you go on to other math courses. So students who might be taking this on their way to a 4-year degree, you're going to have to take a number of math classes. And it turns out that the mixed numbers topic will never appear again in mathematics, okay? However, for students who, for one reason or another, maybe they're in the trades program, maybe they might be reading some sort of historical literature for one reason or another, you might encounter mixed numbers due to the fact that they were in widespread use prior to these modern innovations, because a mixed number will actually allow workers to do the task of measuring out something in the real world. And so, whether you look at stock market charts from the 1930s and everything before the 1930s, or whether you're looking at, say, measuring out gallons on an old pumping system, or whether you're looking at, say, a cookbook recipe and or medieval mathematics, what you're going to see is that the mixed number notation was in widespread use prior to the 1930s and was in fact the de facto way of being able to write out fractional terms for doing useful things. Now, with modern computing and specifically digital electronics, because we can measure a quantity much more precisely than we could even prior to the 19th century, what you see is a move and or a shift away from the use of mixed numbers to the decimal system, which is more or less standard in every math class that you will encounter from this point outward. And so both systems of measurement are very useful to know, depending on the application, but the decimal is more useful. It has more utility in our modern world, especially for students who might be European and or they don't necessarily live in the United States, who have what is known as the SI system of measurement. The SI system of measurement automatically incorporates decimal notation in just the way that it does business. And so both systems are going to be absolutely critical, but probably the decimal will be more important. Nevertheless, how does a mixed number work? Well, suppose that instead of 63 sevenths of a foot, we were actually tasked with asking our worker to measure out 65 sevenths of a foot. Well, just like before, the worker would have to perform the calculation of dividing 7 into 65. But this time, when they go to divide 7 into 65, they know that 7 can go into 65 9 whole times. 9 times 7 gives us 63, and they would be left with 2 remaining. Now, this is what is important. The question is, what does this 2 remaining actually represent? Well, if we're telling a worker that he's going to be measuring 65 sevenths of a foot, that means he's going to have to take a measuring stick that's exactly 1 foot long. He's going to have to slice that measuring stick into 7 equal pieces. And he's going to actually have to take a bunch of measuring sticks, not just a single measuring stick, slice all of these measuring sticks into 7 equal pieces. And then he'll need to assemble in order exactly 65 of those measuring sticks that have been split into 7 equal pieces. And what he's going to find is that he's going to need an additional measuring stick that has been split into 7 equal pieces. And he's going to have to take 2 of those additional pieces, okay, at the end of the day. And so what that looks like in terms of a fraction is that he's going to have 9 whole feet that he's measured out. But then he'll have 1 additional measuring stick that he's going to have to break open and cut into 7 equal pieces. And from this additional measuring stick, he's going to take 2, exactly 2 of the pieces of the measuring stick that has been sliced 7 ways. Okay. Now, the mixed number notation is kind of a shorthand way for us to tell our worker to do this task of, lining up 9 feet and then taking a single measuring stick and slicing it 7 ways and then measuring out the 2 remaining pieces. And so the way we do that is we write our number 9 in big letters, usually using a larger type font, meaning the font for the 9 will usually be larger in a textbook if you see it. And then we'll have our fraction to the right of the number, usually in a smaller font, and it'll be parked next to it somewhere. And so one thing students should be cautious about is that from this point onward, we need to be really, really careful with how we write multiplication of fractions. Some students may have gotten into the habit of, say, using a dot to multiply their fractions. Some students might be sloppy and not have a dot to represent their fractions. They just may park their fractions next to one another. But in both of these cases, I would tell students to really, really watch out. Wrap your multiplication operations in parentheses to make sure that you separate out each of the numbers, because now if a student had written, say, 3 and next to it he had 2/3, we don't know if it's a mixed number, 3 and 2/3, or if he's taking 3 and multiplying it with 2/3. Of course, both of these answers are going to be radically different. And so if we do want to describe the process of taking 3 sets of 2/3 or 3 times 2/3, we're going to need to wrap that fraction in parentheses in order to denote just that. Okay, so aside from that little caution, meaning be careful how you write your fractions, the mixed number notation will always have just some big letter to denote how many parts, how many whole parts of something that we're measuring. So in this instance, our 9 represented feet if we're measuring in feet. Or if we were measuring in meters, the 9 would represent exactly 9 meters of something. And then to the right of this number, we would write our little fraction. In this case, I'm going to use A, B, and C to be any numbers we want them to be. So A could be 5, it could be 10, it could be 10 billion of something. B or C could also be any numbers we want them to be. But the B denotes the remaining fractional pieces. It's our remainder. And C represents the number of equal pieces of that something that we're measuring. So in our previous example, we had cut our foot into 7 equal pieces. Now since we're using these mixed number notation to represent actual measurement, we do need to understand certain ideas when it comes to how you measure an object. First of all, as I stated earlier, in the past, when you actually went to go measure out something, before you had computers and or calculating devices, this was rather difficult to do, okay? And the problem is that whenever you perform a calculation and you get a number that is either really, really small or really, really large, this number is actually meaningless on a practical level if we have no way to measure that object out, which is to say, if you were to ask your worker to build a skyscraper that was 250,000 feet long, that is simply impossible for your worker to do. Okay, that is a ridiculously large skyscraper. That would be larger than any skyscraper that's like 15. It would be more. I believe it would be more than 20 miles long. So that would just be ridiculously big. And if you asked your worker to build you a part or a component for a machine, and you said, "Hey, I need you to build this part to within 5 billionths of an inch," that I'm sorry, that's just simply impossible for your worker to do. It doesn't, it would take an act of God to allow your worker to measure out a part that's as precise as 5 billionths of an inch. Okay. And so the second thing that we need to do, or that we need to understand about measurement rather, is that when it comes to past measurement, precision, the amount of precision of our calculation and our measurement, the precision of a calculation is meaningless without a way to measure an object precisely. So this is to say, you might have some sort of a calculation that has 20, 30, 50 steps, whether it be a thermodynamics problem or a problem where you're calculating the amount of force, the amount of torque an engine can put out. It really doesn't matter how precise that calculation might be. If you don't have a way to measure out that precision in the real world, that calculation is, for all intents and purposes, meaningless. And it's meaningless for the same reason that you might tell a worker to construct something that's super, super large or super, super small. It's just you don't have a way to actually measure that out, so it can't be done in the real world. You would be dealing with metaphysics instead. And so measurement is always relative to one's ability to measure uh, a specific reference. Okay, so for example, I'll just write that down. Measurement is only precise relative to a reference. And so what I mean by this is if we wanted to measure an inch out, exactly 1 inch, well, the precision of 1 inch is relative to our ability to measure a foot, since there are exactly 12 inches in a foot. Or said another way, you would take a measuring stick that's exactly 1 foot long, you would cut it into 12 equal pieces, and you would take one of those pieces, which would then represent an inch. Okay, so since there exists 12 inches in a foot, our ability to measure the inch is relative to our ability to measure the foot. Since there are 12 inches in the foot, we would have to take the thing that's exactly 1 foot long, cut it into 12 equal pieces, and then take exactly one of those pieces, and that is an inch. The situation with the millimeter is much more dramatic, or even the centimeter is much more dramatic, because the centimeter and the meter are because the centimeter and the millimeter rather are both defined in terms of the meter. Your ability to measure out exactly 1 centimeter would mean that you need to take something that's a meter long, you need to cut it into 100 equal pieces. Okay, that's going to be really, really difficult to do. And then you take one of those pieces, and there goes that's your centimeter. Or if you're measuring out exactly 1 millimeter, you need to take something that's a centimeter long. You need to cut it into 10 equal pieces, and there you go. You've got your millimeter. And or you take presumably your meter stick, and you cut it into 1,000 equal pieces, and you take one of those little tiny pieces, one of those little tiny slivers, and there is your millimeter. And so while the Europeans like to brag about how nice, quote unquote, the SI system of measurement happens to be, in all intents and purposes, prior to the 1700s, it would have been virtually impossible to actually go from, say, measuring something that is exactly a meter long to measuring something that's a millimeter long, or measuring something that is a meter and then converting exactly to a centimeter, as this would just be really, really very difficult for people to measure out in any way, shape, or form. It's only with the advent of machining, and specifically precision screw mechanisms, which were invented in like the 1750s. Okay. And then after the 1750s, once you've got precision machining down and you can actually cut out these very, very tiny pieces of something, these very, very tiny slivers of something, only then are you able to say, okay, here's something that's exactly a meter long. Let's go ahead. We're going to create a system of measurement, which is exactly where a unit is exactly 1/1000th of that whole. Okay, and we're going to measure that out. It simply wasn't practical prior to, say, 1750 to do that. Actually, it was impossible to do that. And even after the 1750s, while the SI system of measurement could have certain theoretic value for mathematic operations, especially in certain subjects, such as electricity and or thermal fluids and these kinds of applications, uh, the micrometer wasn't invented until 1848, and the vernier caliper wasn't invented until 1851. And so if you were giving your worker an instruction, you need to cut out this piece of metal and it needs to be precise to like a tenth of a millimeter or a thousandth of a millimeter. That worker just simply couldn't do that. And so he would have no way of being able to complete his task prior to, say, 1851 and or 1848. And even after 1851, okay, it wasn't there weren't enough application cases in widespread use until, say, the World Wars began, where you start seeing military technology advancements, where you needed a lot of precision machining to make your artillery, and or you need precision machining in order to design and build your tanks so that your tanks work and or can be assembled properly every single time. Really, prior to World War I, there just wasn't the emphasis in order to push society in that direction. And really, prior to, say, 1930s, okay, the public, there weren't enough use cases in the public to really demand a major shift to, say, decimal notation in order to represent these calculations. And so as a consequence, this whole idea of being able to measure something, it really was more thought of in mixed number terms. And one of the interesting things of mixed numbers is it does help us facilitate telling our workers how to perform a specific calculation. Again, going back to the feet example, if you told your worker, hey, I need you to go measure out exactly 1 1/2 of a foot. He could grab his measuring stick. He could measure out one measuring stick. There's my foot. He could go grab another measuring stick. And of course, he would be able to cut this measuring stick in half. And there's his 1/2 of a foot. Or more precisely, because the American system has exactly 12 inches inside of a foot, right? The foot has been partitioned into 12 equal units, which we call an inch. Then the worker would automatically know, okay, well, half a foot is exactly 6 inches. And he would have that memorized already. So you wouldn't even have to write 1 foot 6 inches on a piece of paper. You would write simply 1 1/2 feet. Okay. And the worker was supposed to be able to figure out what that meant for you. All right. Now, to convert to a mixed number from an improper fraction, you simply, firstly, you perform division. And then the second step is you write the remainder as a fraction, which we demonstrated. So just as another example, let's say you wanted to convert from the mixed fraction 109/5. Okay. And you're like, what is this equal to? Well, you would have to do the long division by hand. 5 goes into 10 2 times. 2 times 5 gives you 10. Subtract, you get 0. Drop your 9 down. 5 into 9 goes 1 time. 1 times 5 is 5. Subtract, you get 4. And then with this remainder, what you're going to do is you are going to create a new fraction where the remainder is the numerator of the new fraction. And what you're doing with this fraction, in this case 4/5, is we are adding this with however many parts, however many whole parts we have. So in this instance, when we divided 5 into 109, we were left with 21 whole parts with a remainder of 4. So we then can write this 21 plus 4/5 as a mixed number by writing 21, and next to it, we simply write our fraction. Okay, last example. If I wanted to, say, convert 57/3 to a mixed fraction, we're first going to go to the side of our page somewhere. We're going to divide 3 into 57. 3 goes into 5 one time. 1 times 3 is 3. Subtract 5 minus 3 gives you 2. Drop your 7 down. 3 into 27 goes 9 times. 9 times 3 is 27. So it turns out that 57 divided by 3 is exactly 19 with a remainder of 0. So you would have 0/3 or simply 19. And that would be as good as you can get. Let's try a different example. Start here. Suppose you had 59/3. Okay. Just like before, you're going to go to the side of your page. You're going to take 3. You're going to divide it into 59. 3 into 5 goes 1 time. 1 times 3 is 3. Subtract, you get 2. Drop your 9 down. 3 into 29 goes 9 times. 9 times 3 is 27. Subtract, you get 2. So 59/3 as a mixed number, it turns out, would be exactly 19 plus 2 and a third. So 2/3 rather. Not 2 and a third, but 2/3. Where we get this 2 from, this is our remainder that we were dealing with. And we get the 3 from the fact that we were initially dealing with an item that had been cut into thirds. So now we can write the mixed number, 19 and 2/3, as simply a 19 with the 2/3 part next to it. Cool. Suppose that we want to convert from a mixed number back to an improper fraction for whatever reason. And perhaps the reason is that we're going to need to do a bunch of multiplication and or division, addition and or subtraction operations. And of course, the question would be, how do we do this? Well, there are a couple of different ways. Suppose you wrote 5 6/8. Method number 1, which is the long way, would have you convert the mixed number to what it literally represents. The mixed number 5 6/8 represents 5 6/8. So 5 whole pieces plus 6/8. And at this point, we would have to remember that anything is the same thing as itself divided by 1. So 5 is the same thing as 5/1. And now you have an addition of fractions problem. Anytime we're adding a fraction with a denominator of 1 with another fraction whose denominator could be whatever, and we want to find a common denominator, we know that the LCM technique is probably going to be the fastest way to do that or to accomplish that task. And so at this point in time, we're going to take 8/8. We'll multiply it with 5/1 since 8 is the LCM of 1 and 8. This is going to then give us a common denominator. 8 times 1 gives us 8. 5 times 8 gives us 40. So you should have 40/8 plus 6/8. And that's going to give us 46/8. This would, of course, be our improper fraction. Suppose you had another example, 2 5/7. Doing things the long way, you would break open this mixed fraction. You would write it out as literally 2 5/7. You would then have to convert the whole 2 to a fraction. And as you are adding these two fractions together, you need to have a common denominator. So you're going to take your 2 over 1, and we would multiply it by the LCM of 1 and 7, which happens to be 7. You're going to have 7 times 2 is 14. 7 times 1 is 7. 14 plus 5 gives us 19. And this would be our answer. Of course, the question that students might have is there a faster method to converting a mixed number to a improper fraction? And of course there is. So for any mixed number, the following is the formula to convert to an improper fraction. What you're going to do is you're going to multiply whatever the base of the fraction that you happen to be dealing with happens to be, the base of the fraction, C, with A. Then what you're going to do is you're going to take the result of that multiplication and add it with whatever happens to be in the numerator of the fraction. So we're going to add the result, A times C, with B. And then what we do with that with that quantity is this becomes the new numerator of our improper fraction. So as an example of this, 2 and 5/7, this is going to be the same thing as 2 times 7 plus 5 all over 7. It's that simple. 2 times 7 plus 5 all over 7. Now, how did I do that, or how to do that easily? You can think of it as two separate operations. You're going to take whatever number is in your fraction, the base of your fraction, which in this instance is 7. We're multiplying it with 2, and then we're adding the result with whatever happens to be in our numerator, which in this instance is 5. So you're going to do 2 times 7 gives me 14 plus 5. That gives me 19 over 7, which of course is what we had before. Let's see if it works for 5 and 6/8. So previously we calculated the improper fraction equivalent for 5 and 6/8. In this instance, we're going to use the technique that we've learned. We're going to take our base, we'll multiply it with the whole number 5, and then we'll add that result with 6. So we'll do 5 times 8 plus 6, and we're going to do this all over 8. 5 times 8 gives me 40. 40 plus 6 gives me 46. And this is indeed the same result as what we found earlier. All right, guys. That's all I have for you today. Take care.